Assalamualaikum warahmatullahi wabarakatuh and good day everyone. Today we're going to start learning unit 6, Analytical Separation Techniques. In this learning unit, you will be learning 3 things. So at the end of this learning unit, you should be able to first describe and explain the general principles and theory of analytical separation. Number 2, describe and explain the different analytical separation method. And number 3, determine the retention factor of individual component in mixtures of colored compound, which is specifically related to chromatographic separation technique. What is analytical separation? Separation isolate the analyte from potentially interfering constituent so that the quantitative analytical analysis can be obtained. There are 2 common principles of separation. First, complete separation, and second, partial separation. If you look at the first figure on your left, this is describing how complete separation is done. Let's say you have 4 types of compounds in your substance that you want to analyze. Complete separation means you are going to separate all the components of these compounds, meaning to say that all the compounds inside this substance is separated and you can take out each of them for further analysis. What about partial separation? Partial separation means you only take out the components of your interest for analysis. For example, you have the same compound just now, you have the same substance, which has different components, 4 components or 4 compounds in the substance. In partial separation, if your analyte of interest is the green compound here, you are going to separate only the green compound because this is all the analyte that you need for further analysis, and you leave the rest of the compounds not separated. So basically, this is a simple explanation on how complete separation and partial separation works. There are many types of analytical separation method as in the list. We have chemical or electrolytic precipitation. We have learned on chemical precipitation in learning unit 3. That is part of analytical separation technique because we are taking out analyte from one substance using precipitation process for further analysis on further quantification. Another separation method is distillation process, solvent extraction, ion exchange, chromatography, electrophoresis, and low fractionation. However, in this learning unit, we are going to look into details on the 4 analytical separation techniques highlighted in red font, which are distillation, solvent extraction, ion exchange, and chromatography. Analytical separation can be classified based on the techniques of separation, and the techniques of separation can be classified based on the basis of separation. For example, if the basis of separation is by size, these are the examples of separation technique. Let's say filtration, dialysis, size exclusion chromatography. They utilize size of particles or size of the components of the analyte to be separated. So if the basis of separation is by size, you can find some examples of the separation technique, including filtration, dialysis, and size exclusion chromatography. Sometimes, you can also do analytical separation based on the mass and density. Remember, we have learned in Learning Unit 3 about gravimetric analysis. In gravimetric analysis, 3 of the examples that we have learned is on how we determine the suspended solid, dissolved solid, and total solid of a water sample. So the separation is based on mass and density. And another example of separation technique based on mass and density is centrifugation. Centrifugation is a process whereby you apply a centrifuge process to separate the samples into 2 or 3 components based on their density. We have learned the term masking in Learning Unit 3. So this is an analytical separation based on complex formation. There are also analytical separation based on change in physical state, for example, distillation and recrystallization. We are going to take a look into distillation process later on as an example of analytical separation based on changes in physical state. Analytical separation can also happen based on changes in chemical state, for example, precipitation process, ion exchange, electrodeposition, and volatilization. Remember, in Learning Unit 3, we have also learned about precipitation process and volatilization process, which the separation of chemicals or analyte is based on the chemical state. Precipitation process, for example, is based on a solution of your analyte, which you add on a precipitating reagent, and at the end of the process, you will collect the precipitate in the form of solid. So there is chemical changes happening during precipitation process, which involves the precipitation reaction. Another type of separation is separation based on partitioning between phase. The two examples of separation technique based on partitioning between phase are extraction and chromatography. So in this Learning Unit 6, we are going to take a look into both of this process, extraction process and chromatography process as an analytical separation technique. In the first part of Learning Unit 6, we are going to learn about mechanical phase separation. What is the meaning of mechanical phase separation? Mechanical phase separation are separation based on equipment employs mass differences, size differences, or a combination of both to selectively reject undesirable solids and retain desirable solids in any analytical separation process. Sometimes, mechanical phase separation not only separates between solid phase and also liquid phase, but it can also separates between liquid to gas, solid to gas, and other type of mechanical phase separation. There are two types of mechanical phase separation. First, separation based on a change of state, and second, separation based on partitioning between phases. Let's take a look at the first type of separation under mechanical phase separation, which is separation based on a change of state. In this case, when analyte and interferent are in the same phase, separation is possible by inducing a change in one of the physical or chemical states. Examples of change in physical state are from liquid state to gas state and from solid state to gas state, this is called liquid to gas and solid to gas phase transitions. Let's take a look at one example of separation based on a change of state, which is a distillation process. In distillation process, analyte and interferent are miscible liquids with significantly different boiling points. Let's say we have a simple distillation. A simple distillation means this is a process for separating liquids with large difference in boiling points. Can you think of one example of distillation process in your daily life? One of it is the distillation of water from impure water to a pure water. This is an apparatus of a simple distillation process. If you look here, you have a heated sample and you measure the temperature of the sample heated. Okay, so the sample is heated to a point whereby one of the analyte inside can be vaporized, whether the analyte or the interference. Okay, one of it which has lower boiling point will be separated from the compound by distillation process. Let's say you have a mixture of water and hexane in this distilling flask. Hexane has boiling point of about 60 degrees Celsius, but water has boiling point of about 100 degrees Celsius. So what happens when you heat the mixture of water and hexane at 60 degrees Celsius? Will the water vaporize? No. But will the hexane vaporize? Yes. So from this process, the hexane will vaporize and goes up to the upper part of the distilling flask and goes into the condenser. The purpose of having the condenser here is to cool down the hexane or the analyte or even the interference coming into the condenser, so that we can collect the distillate here at the end of the process. Okay, so this is a simple distillation technique. Let's look at another example when you have water, tap water in the laboratory and you want to convert the water into a distilled water. So a distillation process is a process that you use to take out interference from the tap water, for example, solid and anything, by heating the samples to 100 degrees Celsius so that water can vaporize and goes into the condenser, cool down, and we can collect it as distilled water, and all the impurities, all the interference are left out in the distilling flask. Okay, so this is an example of simple distillation. Another type of distillation process is the fractional distillation. One example of fractional distillation is the processing of crude oil. When you have a crude oil, you process them into different products by vaporizing them at different temperature. So at different temperature, let's say for example at 150 degrees Celsius, you will get gasoline or petrol. At 200 degrees Celsius, you will get kerosene. At 300 degrees Celsius, you will get diesel oil and fuel oil at 370 degrees Celsius. But if you heat it up to 400 degrees Celsius, you will get lubricating oil, paraffin wax, and asphalt. So this is a good example of fractional distillation, whereby you can separate different compound at different temperature from a particular main compound. Recrystallization is another example of analytical separation based on a change of state. In recrystallization process, using a minimum volume of solvent, the analyte's solubility is high when the solvent is hot and low when the solvent is cold. This is something that we have learned in Learning Unit 3 when we talk about solubility of a compound or a substance or chemical substance. Okay, so the analyte solubility is high when the solvent is hot and the solubility is low when the solvent is cold. So the interferent must be less soluble in hot solvent than the analyte or present in smaller amounts in order for recrystallization to happen efficiently. The solution is allowed to cool to slowly promoting the growth of large, pure crystals. Now, let's take a look at another type of mechanical phase separation, which is separation based on a partitioning between phases. Based on the selective partitioning of the analyte or interferent between two immiscible phases, this is what we call partitioning between phases. So let's say we have a solute S, which is in contact with a second phase. The solute partitions itself into two phases. Okay, first phase 1 and second phase 2. So at equilibrium, we have distribution constant Kd is equal to the concentration of solute in phase 2 divided by the concentration of solute in phase 1. So if after calculation you find out that the Kd is large, it means that the solute moves from phase 1 to phase 2. And if the Kd is small, it means that the solute remains in phase 1. Okay. So separation is only possible when Kd favor only one of the solute, meaning to say that the solute can move from one phase to another. Now let's take a look at separation by solvent extraction. Separation by solvent extraction involve chemicals, which is solvent. So there are 4 types of solvent extraction, including liquid-liquid extraction, liquid-solid extraction, solid-liquid extraction, and gas-liquid extraction. Let's take a look at a very, very simple liquid-liquid extraction process. So the most simplest liquid-liquid extraction process is using separatory funnel. If you look at the diagram on your right side here, it's a separatory funnel. Okay. So using separatory funnel, two liquids are shaken to increase the surface area between the two phases, and the liquids are allowed to separate after a shaking process, with the denser phase forming the lower layer. Okay. For example, when you want to analyze pesticide in water, you can extract the pesticide into hexane. Okay. Let's say you take a water sample containing pesticide and you put it into the separatory funnel. Second, you put in hexane into the separatory funnel and you mix and shake all those two liquids inside the water and also the hexane just now. Remember, the water contained pesticide and you want to move the pesticides from water into hexane so that later on you can evaporate the hexane and get the mass of pesticide in the hexane for your analysis. Okay, so after you mix well the two liquids, which is water sample containing pesticide and the hexane, you shake them and then you allow them to separate. You put them still, okay, and then the denser phase will be on the lower level of the separatory funnel. So if you look at the darker component here, this one has more density, and phase 2 here, it has less density compared to the phase 1. Okay. So disadvantages of this process is that the extracting solvent are limited to those that are water immiscible only. Right? So this is liquid-liquid extraction. When we talk about liquid-liquid extraction as well, the solute is partitioned between two immiscible phases, as has been discussed just now, which is usually an aqueous and organic solvent. Just now we have one example on water sample containing pesticide. That one is an aqueous phase, and hexane as the solvent, which is the organic solvent. So if the solute is initially in an aqueous phase, which is SAQ, and is extracted into the organic phase, which is SORG. ORG means organic, AQ means aqueous. Okay, so the partition coefficient is KD equal to concentration of the solute in the organic phase divided by the concentration of solute in the aqueous phase. So where do we get this formula? We get this from the partition coefficient equation just now, where we have KD equal to solute in phase 2 divided by the solute in phase 1. Okay, phase 1. All right. So aqueous just now is phase 1 and organic is phase 2 because we want to move the pesticide in a water sample into the organic phase, which is the hexane. Okay, so that's the example. So to know the efficiency of an extraction, we need to know the distribution ratio, which is the ratio of the solute's total concentration in each phase. So D is represented by this formula. Okay. Total concentration of solute in the organic phase divided by the total concentration of solute in the aqueous phase. D is a constant independent of the volume ratio, and the fraction of the solute extracted will depend on the volume ratio of the two layers. So the percent extracted is given by the equation percent E equal to D. D is just now the distribution ratio, okay, and VA is volume in the aqueous phase, and VO is volume in the organic phase. Okay, so this is how you calculate percent extraction. In general, for an identical extractions, the fraction of analyte remaining in the aqueous phase after the ninth extraction is, okay, the ninth extraction is meaning how many times the extraction is conducted. Okay, so this is the equation for quantifying the amount of extraction. Okay, so if you look at the example for liquid extraction here, example of calculation, let's say you have 1 gram of solute is dissolved in 100 ml of aqueous solution. Calculate the amount of solute remaining in the aqueous phase after first a single extraction, means here N is equal to 1. Okay, a single extraction with 90 ml of an organic solvent. Then B, a single extraction, again, a single extraction N equal to 1 with 30 ml of solvent. Okay, just now in A, you have 90 ml of organic solvent, but in B, you have 30 ml of organic solvent. And C, 3 successive extraction with 30 ml of solvent, meaning to say that you have here N equal to 3. Assuming that the distribution coefficient for the extraction is 10, so you have D equal to 10. Okay, so 1 gram here is amount of your solute and 100 ml is the volume of your aqueous solution. So 90 ml, 30 ml, and 30 ml here is your volume of organic solvent, which is VO. Try to use the equation here to calculate your answer, which is the amount of solute remaining in the aqueous phase after extraction. So when you substitute all the equation, all the values into the equation, you will get solution here. So if you look at the equation that we have from the previous slide on calculating how much extraction is happening. So for this question, we know that we will extract for question A, we will extract 1 time, which is N is 1 with 90 ml of organic solvent. Okay, so we know that the initial mass of our solvent is 1 gram. So you put 1 gram here. One gram here is equal to this, Q naught. Okay, so what is the volume of your aqueous solution? VAQ is 100. It's given in the question. D, which is the distribution coefficient, given 10. Volume of your organic solvent, 90. Volume of your aqueous phase, which is 100 gram. So when you calculate everything, you get 0.1 gram extraction. Bukan 0.1 gram extraction, but 0.1 gram left in the solution. Okay. All right. So now you repeat the calculation step for B and C. For B, you still have N equal to 1. So no need to do anything with N because it's only 1. Okay, so you just substitute everything into the equation. And for C, you extract it for 3 times, so n would be 3. So that's why you have here, when you substitute everything into the equation here, you also have to do power of 3, okay, and you get the answer. So from the calculation, you know that 90% of the solute is extracted with 90 ml of solvent. 70%, 75% is extracted if you use 30 ml of solvent one time. But if you use 3 times of 30 ml of solvent, you will extract 98.4%. Which one has the best extraction? Of course, the third one, which is C, when you extract using 3 times of 30 ml portion of your organic solvent. What does that mean? That means that if you have 90 ml of solvent to do this, it's better if you break down the extraction process into 3 times using 30 ml each one time, so that you can get more efficiency in your extraction. Okay, it is always more efficient if you do it more than one time. Okay. Now, let's look at the solid liquid extraction. In solid liquid extraction, the liquid sample is passed through a cartridge containing solid adsorbent. So the choice of adsorbent depends on the properties of the species being detained and the matrix in which it is found. For example, you can isolate sedatives from serum using C18 solid adsorbent. The retained sedatives are eluted from the cartridge by a solid liquid extraction later on using acetone. One of the very simple example that I can give you is the filtration of water using carbon filter in your water filtering system at home. Okay, whether you have whatever brand you are using for your water filter at home, there is a thing that we call a component of the water filter system, which is a carbon filter. So a carbon filter is one example of how you use liquid solid extraction to separate impurities and contaminants from your water, and that's why you get pure water, clean water for you to drink, and all the contaminants are trapped inside the carbon filter. Okay, so the carbon filter is the solid adsorbent, we call it solid adsorbent, and your liquid sample is your tap water coming into your carbon filter. Okay, so that's one very simple example on liquid solid extraction. So in this case just now, we have an example about sedatives, which can be isolated from the serum using C18 solid carbon, solid adsorbent. So if you look at this example, this could be the C18 solid adsorbent, and this could be your serum sample. Okay, so the serum sample goes into the C18 adsorbent, and the sedatives, they are trapped inside. Okay, as I draw here. Okay, let's say the red dots are the sedatives. They are trapped inside the C18 solid adsorbent, and the remaining of the serum goes out. Okay, the filtered serum. This one is the filtered serum. Okay, so what what you have to do if you want to recover all the sedatives inside the C18 adsorbent, all the red dots here, you want to take it out, what do? So you have to do solid liquid extraction using acetone, meaning to say that you have to wash the solid adsorbent here, the black color thing here. Okay, you have to wash it using acetone, and the sedatives will be carried out by the acetone. And then when you evaporate the acetone, you will get your sedatives as the analyte. Okay. So there is an advantage for liquid solid extraction, which is it is easy to use. It has fast extraction time. You need only a small volume of solvent, and this method, this analytical separation method, has the ability to concentrate your analyte. Okay, why do we say that? Let's say you have your analyte with concentration of 5 ppm. You keep on flowing it through the solid adsorbent, flowing in and out of the solid adsorbent. Let's say you come with your original concentration of your analyte 5 ppm, and you keep on continuously um, adding in or flowing in your sample into the solid adsorbent for, let's say, 1 hour. So what you collect in here just now, let's say you are collecting sedatives just now, what you can collect here will be accumulated. It will be more and more and more. So this is how we say that this process can help to concentrate your analyte. Okay, just now your analyte is sedative. So if you keep on flowing for 1 hour, let's say, there are more concentration of sedatives that you can collect in the solid adsorbents. Now, we move to another type of extraction, which is solid liquid extraction. Solid liquid extraction is done as a continuous extraction process, which is you pass the extracting phase through the sample until a quantitative extraction is achieved. So in solid liquid extraction, the solute is transferred from a solid phase to a liquid phase, and that's why it is named as solid liquid extraction. So a simple example that I can think of a solid liquid extraction in the everyday life is when you brew coffee, you are doing actually the solid liquid extraction, which involves the mixing of the solid coffee grounds with water. Okay, so in solid liquid extraction, the extracting solvent here, if you look at the figure at your right hand side, this is an apparatus for solid liquid extraction in the laboratory. So the extracting solvent is in the lower reservoir. Okay, here is the lower reservoir, and it is heated to its boiling point. So what happened when you heat a sample to its boiling point? This is the same concept that we have learned just now in the distillation process. In distillation process, we heat the sample, the mixture of a sample at boiling point of one of the mixture. Okay, so in this case also we use boiling point. When we heat the sample at a boiling point, it will start to evaporate, and after it evaporates, it will move up. Okay, you see the arrow here. Okay, it will move upward to the condenser, where it condenses back to liquid and collects the upper reservoir with the sample held in a porous cellulose filter thimble. Okay. Later on, I will show you the real picture of a solid liquid extraction apparatus. So example of solid liquid extraction apparatus is Socklet extractor. If you look at here is the photo of a Socklet extractor. This is the lower reservoir just now that I'm talking about. So whenever the sample is heated, this is a heating mantle. Whenever the sample is heated, it will goes up to the upper part of the extraction unit. It goes to the condenser. This is the condenser. They go down, goes up the condenser, and they go down to the filter thimble. Okay, so this is a thimble containing your extracted sample. Okay, so the advantages of solid liquid extraction process, it use only small amount of solvent, and it can remove a high percent of solute, and it can be work unattended for a long period. Why? Because this is a closed system and you always have water flowing for your condenser, so there will be no overheating thing, and the solvent here is always recycled back to the lower reservoir. Okay, so this is how solid liquid extraction works. What about gas liquid extraction? So in gas liquid extraction, the liquid is passed through a separator chamber containing continuous gas flow. So in the separator chamber, we have a continuous gas flow, and you pass through your liquid sample for a separation process. The choice of gas depends on the properties of the species that you want to analyze, you want to separate, okay? The species that being detained, which is the species that you want to, separate from the mixture, and the matrix in which it is found. We have an example here. For example, mercury, it can be isolated from the liquid sample, for example, seawater, using argon gas. So heated gas separated mercury from the liquid solution by changing mercury into mercury vapor, okay, in the separation chamber. So the liquid solution is then flushed away to the waste container, and mercury vapor will flow out. Will flow to the vapor outlet. So from the vapor outlet here, you can collect your analyte. In this case, your analyte is the mercury vapor. Mercury vapor, later on, if you pass it through a condenser, it will condense into liquid. Or if you don't pass it into the condenser, it will becomes mercury vapor. So advantages of this process, it is easy to use, it has fast extraction time. So we have looked into three types of extraction, which is liquid extraction. Okay, remember the pesticide example, pesticide in water, and you use separatory funnel to extract them, to separate them. Second one, we have learned about liquid solid extraction, and then solid liquid extraction, and then gas liquid extraction. Overall, we have four, not three. We have four type of extraction. We have discussed two types of analytical separation just now. The first one is mechanical separation. Second one is solvent extraction. And now we go to separation by ion exchange. So from its name, we know that when we do separation by ion exchange, it's about exchanging the ion in our in our solution with another ion, so that we can collect the ion of our interest or the analyte that we want to collect. Okay. So normally ion exchange is vastly used in water treatment process, whereby we have one or more ionic contaminants that we don't want from the water. We can remove them from water by exchanging them with another non-objectionable, or it means that less hazardous ions from the using the ion exchange process. Okay, One of the typical example of ion exchange process in water treatment is that the process that we call water softening, whereby we want to reduce the amount of calcium and magnesium content in the water. As we have learned in experiment 3, I think, water hardness, you know that calcium and magnesium is the species that contributes to water hardness. So in water softening process, ion exchange is normally used as a process to exchange the ion, meaning to say that you collect Ca and Mg from water and you replace it with some other ions that which is not harmful to water. Okay. All right, the applications of ion exchange, it can be used to eliminate ions that would interfere with an analysis. It can be used for concentrating ions from a very dilute solution. It can be used to remove salt contents from the solution. So here is the photo of a simple ion exchange apparatus whereby we use resin, chelating resin as the as the as the um, as the thing that we put, as the substance that we put into the column. Okay, or we call it the ion exchanger. Okay, we put chelating resin as the ion exchanger for our ion exchange process. So there are some advantages of ion exchange process, which is it is easy to use, it has faster separation time, it can remove interfering elements through the ion exchange process just now, and it has the ability to concentrate the analyte. Why it has ability to concentrate the analyte? Because if we look at the example we have previously on what we say about the example of the uh, sedative example just now. Okay, whenever you have an adsorbent, actually you can concentrate your analyte by trapping them in the adsorbent. In this case, it's not the adsorbent but the ion exchanger in the column. Okay. So these are some of the examples of ion exchange. Um, Iron 3 and aluminum 3 tend to co-precipitate with barium sulfate during the analysis of sulfate ion. So passing the solution containing sulfate via a cation exchange resin contain iron 3 and retain iron 3 and aluminum 3 on the resin. Okay, meaning to say that this is about a precipitation process whereby you have iron 3 and element 3 which can co-precipitate with barium sulfate. We don't want co-precipitation to happen. Remember, we have learned about co-precipitation, which is unwanted product which comes together during the precipitation process. So we don't want this species to be together with the precipitate, which is barium sulfate. So you do cation exchange process using a cation exchange resin. So you can trap the iron 3 and aluminum 3 on the resin. Another example is that we have trace metals in natural water. We can collect it on a cation exchange column. And then the concentrated metal ions can be flushed out from the cation exchange column by acidic solution from the resin for analysis. Then hard water, just now I mentioned about the application of ion exchange to remove hardness from water. And then now we move to the fourth type of analytical separation technique, which is the chromatographic separation. Okay. What is chromatography? Chromatography is a technique for separating mixtures into their components in order to analyze, identify, purify, or quantify the mixture or component. Let's say you have the mixture here at your left hand side, the mixture of different components red, blue, black, and yellow. And after that, you separate them into the four components, yellow, black, blue, and red. So after that, you can analyze each of the components, identify them, purify them, or quantify them. So these are different applications or different usage of separation process, especially for chromatography separation. Chromatography is used by scientists to analyze the analyte or the compound. Okay, what is analyze? Analyze means you examine a mixture, its component, and their relations to one another. Chromatography analysis is also used to identify, which is to determine the identity of a mixture or components based on non-compounds. Chromatography analysis also used to purify sample, which is to separate components in order to isolate one of interest for further study. Okay. Or for quantification, meaning to say that you determine the amount of a mixture and or the components present in the sample. So these are four different applications or usage of chromatographic analysis. These are the types of chromatography analysis. We have liquid chromatography, which separates liquid sample with a liquid solvent. Okay, liquid solvent as the mobile phase, and a column composed of solid beads as the stationary phase. Second type of chromatography is the gas chromatography, whereby you separate vaporized sample using carrier gas. Okay, so this is all about gas. You vaporize your samples and separate it with carrier gas as the mobile phase, and a column composed of a liquid or of solid beads as the stationary phase. Okay, we'll learn after this what is the meaning of mobile phase, what is the meaning of stationary phase. All right, so right now we just want to know what are the types of chromatography analysis available. We have paper chromatography, which separates dry liquid samples with a liquid solvent as the mobile phase and a paper strip as the stationary phase. We have thin layer chromatography, which separates dried liquid samples with liquid solvent as the mobile phase, and a glass plate covered with a thin layer of alumina or silica gel as the stationary phase. Okay, you have heard more than 4 times about mobile phase and stationary phase in this slide alone. So what is stationary phase? Stationary phase is a phase that is fixed in place, either a column or on a planar surface. Okay. Stationary means it doesn't move. Okay. It is fixed in place. So this is what we call a stationary phase. Okay. A mobile phase is a phase that moves over or through the stationary phase, carrying the analyte with it. Okay, you imagine the stationary phase as a road, and mobile phase is the car that travels on the road. If you can imagine it like that way, all right? So again, the stationary phase is a phase that is fixed in place, either in a column or a planar surface, and a mobile phase is a phase that moves over or through the stationary phase, carrying the analyte with it. Another term, important term that you have to know for chromatography separation technique is the term eluent. Eluent is a solvent used to carry the components of a mixture through the stationary phase. Okay. So this slide is basically just showing you about different type of chromatography analysis or chromatography separation. Chromatography itself, it can be divided into two parts, gas chromatography and liquid chromatography. This is divided into two types based on nature of the mobile phase. Okay, and gas chromatography itself can be divided into two based on their stationary phase. If you have liquid stationary phase, you also have another one which is solid stationary phase. What about liquid chromatography? Liquid chromatography has three different nature of stationary phase, which is the liquid stationary phase, bonded liquid, and solid stationary phase. Okay, so at the end of this, we have different instrument that is associated to gas chromatography based on different nature of mobile phase, different nature of stationary phase, different mechanism of separation, and different technique. Technique here means whether it is using column as the stationary phase or it is using planar as the stationary phase. All right, so these are the different instrument that is available for chromatographic method. You will come across later on in your study or in your life as a chemist, these different instrument. For example, gas liquid chromatography, gas solid chromatography, classical liquid chromatography, thin layer chromatography. Thin layer chromatography we will take a look after this, and we also have a high performance liquid chromatography, high performance thin layer chromatography, classical liquid solid chromatography, high performance liquid chromatography, high performance liquid chromatography, paper chromatography, and so on. So many things. But in this learning unit, we are going to take a look into two simple chromatography method, which is thin layer chromatography and paper chromatography. Okay. In chromatography separation happens based on the differences in partitioning behavior. So partitioning behavior also called migration rates, okay, between a flowing mobile phase and its stationary phase to separate the components in a mixture. So column holds the stationary phase and the mobile phase carries the sample through it. Okay. Basically, how chromatography separation works is that sample is loaded onto the polar stationary phase. Okay. Normally, the stationary phase is polar. Okay. And polar compounds will absorb onto the stationary phase to a greater extent than non-polar compounds. So based on this theory, okay, the mobile phase or the eluting phase will help to push or elute the compounds either down a column for a column chromatography or up a plate for thin layer chromatography. Remember just now, the column and the plate represents the stationary phase. Okay, understand that there are two types of stationary phase, column or planar. So for planar, normally we call it a plate. Okay, whether it is a TLC plate or paper for a paper chromatography. So the main concept is to consider the polarity of your stationary phase. Okay. and as well as your eluting substance or eluting compounds, and as well as your uh, compounds of analytes or compounds that you want to analysis, okay? Then you want to separate. All right. In a thin layer chromatography, the stationary phase is just now, as has been mentioned, are made of either silica gel or alumina. Okay, so silica gel and alumina are polar compounds, right? So how do we discuss the chromatographic separation based on the polarity and intermolecular attractive force? Okay, it's easy. The concept is more polar compounds will be more attracted to the stationary phase just now. In the case of TLC, we have silica gel or alumina. Okay. More polar compounds will be more attracted to silica gel than non-polar compounds due to the intermolecular attractive forces, okay, which is a dipole-dipole interaction. The more non-polar compounds will travel more easily and more quickly through the stationary phase. Remember the two concepts here. Let me just underline it. More polar compound will be more attracted to silica gel, meaning they will move slowly. More polar compounds will move slowly. But non-polar compounds will travel more easily, meaning to say non-polar will move quickly, okay, through the stationary phase. Okay, and the mobile phase helps carry the compounds through the stationary phase, and the separation of compounds in a mixture is possible because different compounds have different polarity. Non-polar compounds will elute first and polar compounds will elute last. So you remember this statement, non-polar compounds will elute first. Why? Because they move more quickly compared to the polar compound. Polar compound will elute last because more polar compounds will be attracted to silica gel compared to non-polar compounds. Now, this figure represents a column chromatography. Okay, and what I want to explain through this slide is that components that are weakly retained by the stationary phase will remove through the system more rapidly. Which components will be weakly retained? Based on our explanation just now, which component? The polar compound or the non-polar compound? Right, non-polar compound. Okay, non-polar compound are weakly retained by the stationary phase and they move more quickly, more rapidly, right? Throughout the stationary phase. So if you look at the example here, let's say you have compound A, compound B, compound C. Which one is more polar? A, B, or C? If you look at the speed of these three compounds moving through the system, moving through the stationary phase, you can say that the most polar compound is A, followed by B, followed by C. Okay, the more non-polar is C. The most polar is A. Why? Because A move more slowly compared to B and C. C move the fastest, so we can say that it is the most non-polar of the three compounds. So because the most non-polar compounds move more quickly, it will be eluted first. So C here will be eluted first. Now let's discuss paper chromatography. Paper chromatography is one of the simplest form of chromatography separation method. It is a method for testing the purity of compounds and identifying substances. It's very useful because it is relatively quick and requires very small quantities of material. When you use instrumentation, you have to prepare more samples to be analyzed because you are using instruments, so you need more samples. But in paper chromatography, you merely need a dot of your sample for analysis. All right. So in paper chromatography, substances are distributed between a stationary phase and a mobile phase. The stationary phase in the case of paper chromatography is a piece of high quality filter paper or porous paper. So when we talk about paper, it contains cellulose. Okay. As the stationary phase, and the mobile phase is the developing solution that travels up the stationary phase, carrying the samples with it. Let's see why we say it's traveling up the stationary phase. Yeah, let's look at the figure on your left hand side, as well as the schematic diagram on your left hand side and the real figure on the right hand side. So this is an example of a paper chromatography. It's very simple technique. What you have to do is to prepare one high quality filter paper or porous paper. You label the um, starting line. So this would be the starting line. Okay, starting line here, and you label the finish line, starting line, finish line, and then you set up a beaker with a lid for closing the beaker, okay, to avoid your mobile phase from evaporating. So this is the system for a paper chromatography. Okay, so in a paper chromatography, this here, the red, blue, and light blue and brown sample here, brown dots here are the ink spots. Okay, you dot your samples on the starting line. The ink spots should be centered and evenly spaced on the starting line. If you notice, the line and the ink dots must be above the liquid level in the beaker when paper is placed in contact with the mobile phase. Okay, if you look at here, you have starting line over here. Okay, but your liquid level is over here, slightly below the starting line. We want the liquid level to be below the starting line so that our sample, which we have dotted on the starting line here, will not be affected by the mobile phase, by the solution. Okay, so that the ink there will not be washed out into the liquid by the solution. Okay, so again, the cross section of your paper chromatography, you have the starting line, you have the finish line. The finish line is called the solvent front, or after the solvent reach the finishing line, you call it a solvent front. The ink spots have eluted or moved with the solvent front. If you see at the diagram here, all the dots at the starting line just now, they have moved up the stationary phase or the paper chromatography. So this is why I said just now, the sample move up the stationary phase. It really moves up. Okay. So this is the theory behind a paper chromatography. A small sample of a mixture is placed on porous paper, which is in contact with the solvent. and the solvent moves through the paper due to capillary action. So it moves up because of the capillary action and dissolves the mixture spot. So the components of the mixture with a stronger attraction to the paper than to the solvent will move more slowly. And the difference in the rates with which the components travel along the paper leads to their separation. So the difference in rate here, if you remember just now, we talk about migration rate. Okay. And migration rate depends on the polarity of your sample. So these are the principles for paper chromatography. First, the capillary action. Capillary action refers to the movement of liquid within the spaces of a porous material due to the forces of adhesion, cohesion, and surface tension. The liquid is able to move up the filter paper because its attraction to itself is stronger than the force of gravity. Another principle is the solubility principle, which is the degree to which the solute dissolve into a solvent. Solutes dissolve into solvents that have similar properties, and this allows different solutes to be separated by different combinations of solvent. Separation of components depend on both their solubility in the mobile phase and their differential affinity to the mobile phase and the stationary phase. So these are two of the factors that contributes to the separation of the components. First, the solubility of the mobile phase, and second, the differential affinity to the mobile phase and the stationary phase.